This is Mrs. Murphy from Weber State University, and today we're going to be discussing some data structures. We're going to show you about arrays, links, stacks, queues, trees. We're also going to show you some algorithms for searching and for sorting the data in our data structures. Now, in the database chapter, we talked about data being just a collection of information. The information is stored as tables in the database, but a table is not the only way you can store information. What if we have, say, a shopping list? That's data. Do you really need a table to store that information? You really want to spend the time to write all that information about each item that you're going to be shopping about? Or do you just want to jot down a list as you head out to the store? Well, a data structure is just a generic term for a way of organizing the data. One way you can organize your data is in an array. An array is a type of list, not a random list. You can have a list of animals, a list of food, a list of numbers. It's usually a list of things that are in some way related. In your grocery list, you have a list of items that you're shopping for. You're not going to be listing a random monkey in that list. And suppose you're listing lotto numbers. You're not going to list tiramisu. Tiramisu, that's just kind of a fun word to say. But you get the idea. The list usually is a list of items that go together. So an array is all the same type of information. Numbers go in numbers lists, texts go in texts lists, animals go in animals lists, and so on. It means the list contains values of the same data type. Now these are all numbered lists. Wait, this is a computer class, right? What is wrong here? What's wrong with this list for the computer class? What number do we start counting on? Yep, that's right. All of these lists start at the number 0. Now, a computer has memory to store this information, and if that information is stored in an array or in our list, then the information is stored sequentially in memory. Now, because the array is stored sequentially, it needs to know how much memory it can use up. So for an array, you have to specify the size of the list. Once that list size is set, you cannot change the size without deleting all the information out, resizing it, recreating it, adding all the information back in. So usually you don't resize arrays. It's okay if you don't use all of the positions in the list. They can just remain with no value, or what they call null. Now the code at the bottom of the screen states that this particular list is going to be a string. To a computer, that means text or letters or a combination of letters and numbers. That's any kind of text is what they call strings. The name of the array is fruit. Now the name is for humans to understand. The computer doesn't really care that the list is called fruit and holds fruit. It doesn't even know what fruit is. The programmer will see the name fruit and know, oh, this list should contain fruit, because as humans we do know what fruit is. It makes the code easier for us to read and to debug if it has descriptive names instead of just random names that you think of or random letters or something like that. But as far as the computer is concerned, it just needs a name, and you can put random letters in there for the program to still work. It's just nice to have for us humans. Now the little square brackets after the name of the array indicate that this list is actually an array. The new keyword creates the array and sets the size. That's why it has a little 5 in the square brackets on the right hand side. It says this array is going to have 5 values. Since the array is a fixed size, your array has to have a lower bound and an upper bound. The lower bound is usually 0, because every number we always start counting at 0. It's computer class. Now the upper bound is the highest position that can be used. Since our array is size 5, and we know we start counting at 0, the last position available is actually 4, which is the 5th value. You know, on account we started counting at 0. Now, as we said before, you name the array you want a descriptive name. You don't call lotto numbers with the name bananas. You'd call it lotto numbers. And now notice the lack of spaces in our lotto numbers list. You could use an underscore, but us programmers, we're kind of lazy. Oops, did I say lazy? I mean efficient. We're kind of efficient. We don't want to have to type an underscore. That involves stretching our pinky finger. So many times we use what's called camel case. See that N for numbers? That's like the hump of the camel that makes the next few words or letters stand out as a word. Well, I guess our camel is actually a Bactrian camel instead of a dromedary camel, since we have the L as for lotto numbers, so it's a two-humped camel in this case. But you get the idea. Camel case is the uppercase letters for the humps of the camel. Some programmers use what's called Hungarian notation along with their camel case. That's when you add the letter in front of the variable. The letter just tells it what the data type is. A for array, I if it's an int, like whole numbers. So if we want to create a list of lotto numbers, we would say int, because this time it's whole numbers, then the name, A lotto numbers, equals new int 6. 6 being the number of balls that would fit in our little Powerball list of lotto numbers. The position of those numbers are going to be 0 through 5. Now the new keyword is setting aside that much memory to be reserved for the array. Now really all those position values are memory addresses. That's why the position values have to start at 0 in our list. The name of the array is just the position in memory where the array begins. We use the position values because it's easier for us humans than using those darn memory addresses. Although you have learned hex now. The way you access the values in the array is by using the position variable. Suppose we want to change bananas to, say, mangoes, a more superior fruit in my opinion. All we have to do is set position 2 in the array equal to mango, and that position value is what allows us to access that position 2 in the list and change it to whatever we want. Now a list is great for storing one-dimensional items, such as a list of lotto numbers or grocery items, but what if we were programming, say, tic-tac-toe? What should we store all those X's and O's in? And how about the data in Connect 4 or Battleship? Sorry, I'm showing my age again with these old school games, aren't I? So anyway, I use these particular games as an example because they're a good visual demonstration for a multi-dimensional array. Really, they are just an array of arrays, but that's confusing to think about. So just think of a grid system. There's rows and columns, and in that order. So if I wanted to create this multi-dimensional array, or this table in code, I would use the data type of int for whole numbers, since all of the items in my little table up there are whole numbers. I'm going to name it A data, A for array, and then the capital D for the camel hump. But this time, instead of one set of square brackets, I'm going to use 2 sets of square brackets. One set of brackets for the row and one set of brackets for the column. Now, since in this particular set of data there are 3 rows and 4 columns, I'm going to specify the size to be 3, 4. So it's always rows, columns. Now I want to get a particular value. Instead of a position variable, you use the row and column numbers to get the data. So I have an int value and I set it equal to row 2, column 1 at the data. That means that particular variable, that int value, has the value 9 from my multi-dimensional array. Now you can get more complex with 3-dimensional arrays. There's even 4 and 5-dimensional arrays if you want, but that's just getting too confusing. There's more efficient data types out there, so it's rare to see a 3-dimensional array or higher. But it works the same way, but instead of rows and columns, you have rows, columns, levels, whatever the next section is. It depends on your data. So the advantage to an array is you can store multiple items in a single name. Data can be accessed directly using an index value. Now there are a few drawbacks to the array. That is that it's a fixed size, so you can't just add and delete items very easily, especially if you exceed the size of the array. Another disadvantage is the fact that all the memory locations are sequential, so it uses up a large chunk of memory. A linked list is another list, but unlike an array, it's dynamic in size. It's because the memory locations to store the data are not sequential. They're stored all over the place. Wherever memory can be allocated, there you'll find some part of your linked list. Well, each piece of data in your linked list is called a node. And a node has 2 parts. It has the data that's getting stored, but then it has a memory address or a pointer to where the next node is located. The end of the list can be found when the pointer for the next node is set to null or no value. If you wanted to insert data into a linked list, all you have to do is change the next pointer. First, create a new node of data and make sure you have the next pointer point to whatever item you want to be next in the list. And then change the previous node's next pointer to point to the new node. Voila, it's now in the list. The same is true for removing a value in a linked list. All you have to do is take the previous node's next value and set it equal to the node's next value that you want to remove. Then you can delete the node without breaking the chain of linked nodes. With a linked list, you still have a list of items with a single name, just like an array, but the big advantage of a linked list over an array is its dynamic in size. It's super easy to insert and delete information. All you have to do is just change that next pointer to point to a different node, and it'll skip over one. Or if you want to add some piece of data, you can have your next pointer point to the new node and have the new node point to the next node in the list. It's super easy to add and delete in a linked list. It also uses less memory since data is stored in small pieces throughout your memory. One thing you do lose with a linked list over an array is you no longer have direct access to the data. With an array, you could access each item just by its position value. But with a linked list, you have to get the data from the middle, and you want to get the data from the middle, you have to start at the head of the list and traverse all the way to where you need. They've tried several things, including you can have a doubly linked list. That way you can go to the previous node, and that kind of helps, but you still don't have direct access to the data. Well, because of this, they have another data type that aids specifically in searching for information. A tree is a hierarchical structure. Once again, it has pointers to organize the data. There's a root pointer that shows the top of the tree is located, and each piece of data is still called a node. Just like in the linked list. But this time, instead of having a pointer to the next node in the list, it has pointers to all of its little children nodes. Now, if a node doesn't have any children, such as that K down there kind of at the left bottom side, then it's called a leaf. They really go with that tree theme, don't they? An example you've seen of a tree is that of a file structure. When you click on your Documents folder, that branches up and allows you to select all the children nodes. And if you select another folder, that opens up and branches out and finds the files. Until you keep going, until you keep branching it down the tree until you find whatever it is you're looking for. Now they have a tree that's specialized to optimize in searching. This is called a binary search tree. Now with this kind of tree, each node can have a maximum of 2 children, a left child and a right child, thus binary, 2. The right side is always larger than the parent, and the left side is always smaller than the parent. So if you look at the root node, that's that 20 up there at the top, and then look to the left and right of that node, the right child has a higher value, and the left side has a lower value. But if you look at the left and right child of that 10 on the left-hand side, the child of the 20, it's the same way. The 5 on the left is smaller and the 15 on the right is larger. Now it makes it super efficient in searching. Since we're going to search for, let's try and search for a value. Search for the number 27. You're going to start at the root of the tree. Since 27 is greater than 20, you need to go right. That's because we know the child node to the right is higher. So then we look at that 30. Well, since 20 is less than 30, we need to go left. Now we're looking at the number 25. Go right again, we find the number 27. That only took 4 comparisons to find the value we're looking for. So the height of the tree is the maximum number of comparisons it will take to find any value in the tree. Compare that to a linked list where you had to start the search at the head node and continue down every node till you find the value you're looking for. Okay, let's show you how to add some nodes to a binary tree. We're going to add the following data to the binary tree, and in this particular order. We're going to add 20, 10, 5, 30, 15, 25, 42, 45, 27, 23. Okay, so first let's add the 20. This first one's easy. Whatever you add to the tree first becomes the root of the tree. So now let's add the number 10. We know that 10 is less than 20, so it becomes the left child. Okay, now to add the 5. Still, you have to start at the root of the tree. We know we need to go left as 5 is smaller than 20. And then we find our 10. Since 10 doesn't have any children, so 5 is going to become the child node on the left-hand side of 10. Okay, now we're going to add 30. Since 20 doesn't have a right node, 30 is going to become the right child of 20. Now for the value 15. We're going to still start at the root, and 15 goes to the left as it's smaller than 20. However, 15 is larger than 10, so it becomes the right child of 10. Now 25. We're going to go right of the 20 and left of the 30. 40 is going to be right of the root and right of node 30, and since there's not a right child, 40 becomes the child down here. All right, for 45, we're going to go right at 20, right at 30, and it becomes the right child of 40. 27 goes right of the 20 and left of the 30, and it becomes the right child of 25. So you can see how it's adding information kind of builds out the tree. So a binary tree definitely has some advantages over a linked list. Adding is still pretty easy, searching is easy, there's less traversing in the list, and you still have small pieces of data instead of a huge block of data like you have in an array. Now the disadvantages are the shape of the tree. If the tree is really lopsided, it's going to be less efficient. For example, what if you enter the numbers 0, 1, 2, 3, 4, 5, 6 into that binary search tree? It basically becomes a linked list, and each node just points to the next. Just every node has a child node that's to its, and if that makes sense. Searching would be less efficient than a linked list in that situation. So a binary search tree depends on the order that the data is added on what the efficiency of the data structure is. Now a stack is another type of list. It's kind of logically set up like a stack of plates or something. The data is always added to the top of the stack, and it's removed from the top of the stack. This is what's called LIFO. LIFO stands for last in, first out. Okay, so here I have a weird example to show a stack. Imagine a cave, the Bat Cave, or some sort of tunnel that's only wide enough for one car, and there's only one way in. So we're going to have a maroon car go in, followed by a red car, then a blue car. Now the cars want to come out. Well, the only way they can get out is to back up. Which car is going to come out first? Oh yeah, it's got to be the blue car. That was the last one in. There's no way they can turn around, so that car has to get out. Then the red car can come out, and then the maroon car because it was the first in. So an obvious thing that's programmed using a stack is an undo operation on a computer. Most applications, such as word processing documents, they keep track of all the operations the user does. A stack is the perfect data structure to store these operations. When you decide to undo an operation, it just pops that information off the stack and undoes what it did. If the user chooses to undo a second time, it just pops the next operation off of the stack, which is just the previous operation. Let's get you a data example this time. When you add to a stack, you're going to use the push command to put items onto the stack. So I could push 34, and then it would put on 34 at the bottom of the stack. Now, once again, we have a stack pointer, and that keeps track of the top of the stack. The stack pointer, it's pointing at the top and the bottom because there's only one item in the stack, but it's pointing to that 34. So now I'm going to push 21 onto the stack. It's going to go on top of the previous number. The stack pointer now moves up to the top of the stack. Now push 42, that's added to the stack, and the stack pointer moves up. So now I have a stack of 3 numbers with the last number on the top of the stack. The command to remove an item from the stack is called pop. So if a pop command is made, it's going to remove whatever the stack pointer is pointing to, which is always the top of the stack. I'd be left with a stack of 2 and 21 being at the top of the stack, and the stack pointer is now pointing back to that 21, which is on top of the stack. A queue is another list of data, and this time instead of LIFO, we're going to use the acronym FIFO to describe it. That is first in, first out, because the items are logically added to the end of the queue and removed from the front of queue. Think about waiting at line at Disneyland. You got to get into the back of the line, and you have to wait till everyone in front of you has gone through the ride, and when you're first in line, they call you out of the line, and it's your turn to go down Space Mountain or Thunder Mountain, whatever you're going down. Well, At least that was how it was when I was a kid. Now you just pay money and get a fast pass, and now my entire example is just completely... Okay, pretend you're waiting at line at the bank. No fast passes here. All right, so one item that you've seen programmed with a queue is a printer. There's a printer queue that's used for all of the print jobs that a printer needs to perform. As you send an item to the printer, that data is stored into the printer queue. And when the printer goes to process the jobs, it removes from the front of the queue and processes that job. So the jobs are performed in the same order that they're received. You ever have a job fail on you and now the printer won't print anything else? Well, that's because the printer can't access anything except for the front of the queue, and if that job's messed up, you have to go through and manually remove it before any of the other jobs can be processed. Now, queue has two pointers. The head pointer is in the front of the line, and the tail pointer is in the back of the line. That sounds obvious, doesn't it? Well, when the queue is empty, both pointers are not pointing to anything. They have null values. They use the word in queue to add to the queue, and dequeue is used to remove from the queue. So we're going to do names this time. We're going to enqueue Athena. So now both pointers are pointing to the only item in the list, which is both the head and the tail. So now we're going to do another name. We're going to enqueue Brittany. The head pointer stays there, but the tail is now pointing to the end of the queue, or to Brittany. Now if we add another person to this queue and Carrie is added to the end of the line, and the tail is still keeping track of that end of the line. Okay, so now let's dequeue a person who gets removed. Well, the head is in charge of that. It's going to remove Athena. And now the head's going to point to the new start of the queue, or to Brittany. A linear search can be used on an array or a linked list. The data doesn't have to be in any type of order for this algorithm to work. And as the name entails, a linear search just searches in order from the beginning to the end to find the search item. Suppose we're looking for the number 12 in an array. We're going to start searching at the position 0. No, that's not it. And we're going to check the next position. Nope, that's not what we're looking for. We're going to keep going down the line until it finds the number that we're looking for, 12. In this case, in order to find that item, it took 9 comparisons. A binary search can be done if the array or list is in order. Suppose we're searching for the number 57. All you need to do is find the midpoint of that list and check that value. In this case, we have 28. We know that 57 is larger, so we can disregard the entire first half of the list. Now, though, we find the midpoint of the list that's left. We're going to get 63. Well, we can disregard the second half of the list now. Usually, when you find the midpoint, it truncates down to the left side, so we're going to check the number 42. Nope, not in that half. If you go to the right-hand side, we've now narrowed the entire list down to 57. So a binary search can find data in the list just as fast as if it were stored into a binary search tree. Just your data does have to be organized in an order. As you can see by the binary search, it's a little bit more efficient to find what you need if the data does have a type of order. So sorting the data does just that. It's going to put data in order. When a computer sorts data, it can only compare 2 numbers at a time. This goes back to our binary logic and our gates and all that. Remember when it makes decisions, it uses a gate with 2 inputs and returns 1 output. In this case, we can give it 2 numbers and ask which one is greater than the other, and it can return back to us a true or false answer. Now, there's different algorithms you can use for sorting. Some are more efficient than others in certain situations, and it's because when the computer uses its processing power, it takes more time. So the more number of comparisons an algorithm uses to sort the data, the less efficient the algorithm. So today we're going to discuss the selection, the bubble, the insertion, the quick sort. Actually, I'm going to just discuss the selection sort, and then I found some Harvard videos for you guys to learn the other ones. After about 50, 60 animations on one slide, I decided there's got to be an easier way, and the Harvard ones are actually pretty good. So we're going to show you the selection sort, and then go watch the Harvard videos to learn how to do the bubble and the insertion and the quick sort. Okay, we're going to start off with the selection sort. We're going to sort this list from lowest to highest. To do this, we're going to search the entire list for the highest number, and then we're going to put that highest number at the end of the list. Well, to find the highest value, we're just going to start out by setting a variable equal to the first number in the list. In this case, our highest number is 25, just because it's the start of the list, not because it's the highest number in the list. Okay, so now we're going to check that number against every other number in the list, starting with the 15. Since 25 is greater than 15, the statement's true, so we don't need to do anything. 25's already our highest value. Let's check the next number, 12. That's also a true statement, so we don't need to do anything. Now we're going to get to the number 42. And since we found a number larger than 25, this gives us a false statement. 25 is no longer the largest number. Since that's what we're looking for is the largest number, we simply set our variable to the new value of 42. Now we're going to keep going. We're going to keep searching, and we find the value 81. Oops, 81 is larger than 42. It returns a false value. So 81 becomes the largest value. Then the computer checks the last number, has to check all the numbers just in case, even though we can obviously see, but well, that last number is going to return true, and since we've now met the end of the list, we've found that our largest number is 81. Now that we have the highest number, all we have to do is swap the highest number, which is at position 4, with the position at the end of our search area. Now we have one number in order, so we got to do this all over again. But this time we're going to stop short of the end because that's already in the correct spot. So our search space is going to be one less. So we're going to once again set our variable highest to the first number in the list, 25. Obviously it's not the highest number, but that's what we're starting at. We're going to compare it to the rest of the numbers in our search space, not the end of the list. Well, 25 is greater than 15, so that's a true statement. 25 is greater than 12 as well. 25 greater than 42 gives us a false statement, so our highest is now 42. Then we're going to compare 42 to 13, and 42 is still the highest number, and we're going to stop here because this is our search space. We already know that 81 is the largest number, so we're going to leave that number alone. So now that we've found the highest of our search position is 42, we're going to swap that 42 with the value at the end of our search space, not at the end of the list, at the end of our search space. And now we have two numbers in order. So now we need to do this all over again, but this time we're going to stop two numbers short from the end. Our search space gets smaller. So 25 compared to 15, so far 25 is the largest. Compare it with 12, that's still true, it's still the largest. And with 13, 25 is the largest value this time. So since we have that 25, we're going to swap the largest value with that on the end, or in this case the new end, the end of the search area. Okay, so the search space gets a little bit smaller now. Our highest value starts out as the first value in the list, this time 13. Compare that to the 15 and we get a false. So 15 now becomes the highest value. Well, 15 is larger than 12, so we know the 15 is the highest value in the search space. We'll just swap that 15 with the last position in our search area. And now we have a little tiny search area of two values. So we're going to find that 13 is the largest, since 13 greater than 12 is a true statement. So we're going to swap that 12 and our 13, and now our list is in order. Okay, good luck with the rest of the sorts. Those Harvard videos are pretty dang good, a lot better than my crappy animations in my PowerPoint. So I'll put the links on Canvas to kind of show you how those sorts work, and then the assignments are now posted. Good luck with the homework.